great. I guess we can kick off. Welcome again to the one that just joined. Welcome to today's online live demonstration of Twin Fabrica. I am Andrea, Head of Business Development here in Newtwen, and alongside my colleague Alvaro. I am really excited to walk you through our approach methodology to real-time virtual thermal sensing and how we go from simulation all the way to deployable virtual thermal sensors in any motor real case. Before diving into the demonstration, maybe we can give you a quick overview of who we are. We are Newtwen. We have been around since 2020. And we were born as a spin-off of the University of Padova, where we are actually based. We have been growing since, and we have now a team of 25 people and counting. Our core expertise lies in thermal management for ePowertrain applications, where we developed a unique technology that blends physics-based modeling with embedded software. What makes our software, Twin Fabrica, a real added value for our customers is the capability to transform complex thermal simulations into real-time virtual sensors that run on embedded system. Why do companies need virtual sensors in the first place? Because thermal management remains a major bottleneck in the design and control of ePowertrain components. In fact, traditional sensors like NTCs cannot be placed exactly where the hottest and most critical points are, like, for example, the rotor magnets of the machines or the junctions of power modules. On top of that, most commercial simulation tools are simply not designed for real-time use. They require extensive expertise and are often not scalable across different components. These challenges usually result in conservative derating strategies, lower performances of the components, slower innovation, and eventually reduced cost opportunity of the component in the market. This is actually where Twin Fabrica, our software solution, comes in. Our end-to-end virtual thermal sensing platform, which is designed to go from CAD geometry to optimized embedded code. The workflow that we will see in a second with Alvaro includes non-linear parametric model order reduction, data-driven calibration, and has been designed with a white box modeling approach. Everything is optimized for accuracy and real-time performance, which eventually allows the engineering teams to validate, control, and monitor thermal behavior where it matters the most. Here you can see a few key use cases where our technology is already being applied and adopted. This includes inverters, onboard chargers, and of course eMotors, that it will be the focus of today's demonstration. Keep in mind that the workflow and the benefits of this technology are potentially and can potentially be applied in any e-system component. I would like to pass the word to my colleague Alvaro, that will start showcasing the software capabilities. Before he kicks off with the demonstration, feel absolutely free during the demo to drop question in the Q&A section that you see on top of your screen. So at the end of the demo, we will be more than happy to answer all of them.
Thank you, Andrea. And I'd say hello, everyone. Thank you for your time today. I am Alvaro, and I'm here to walk you through our software Twin Fabrica and explain capabilities. So let me start by sharing the screen. Let's see. Let's wait a couple seconds. And yes, our goal for today is not to do a demo, but rather to showcase the complete workflow of Twin Fabrica and highlight the competitive advantage that set us apart in the industry. Twin Fabrica is an all-in-one solution that bridges the gap between complex thermal simulations and real-world applications. And for the showcase, as you might expect, I have loaded already in Twin Fabrica a project of an electric machine. And we're going to go through it together for the configuration of the model until we can finally explore the high-fidelity model, which is real-time feasible. This model can then be implemented in a microcontroller for real-time temperature monitoring, ensuring functional safety and improved current control. So let me start by showing you how easy it is to get started with Twin Fabrica. The journey actually begins within the project panel, and this is a quick start menu that contains all the steps required that take you from a 3D CAD model to a piece of firmware that represents the virtual thermal sensors of your component. Those sensors can then be used for real-time temperature monitoring, as I was mentioning, or control purposes. The main steps to be performed are some import of the files that we have, defining your finite element model problem, reduction, calibration, simulation, and finally we will have the export. But we will go through these steps one by one in this showcase. The software contains all the necessary pieces of technologies needed to transform your high-fidelity models into a piece of executable code which is real-time feasible. And the first component is finite element analysis. And as you may know, in order to run a finite element model to simulate it, we need three main components. So if we move to the first physics window, we will find the first component that we require, which is the CAD kernel. This is the backbone of our system, and it allows you to seamlessly integrate and review your 3D CAD models inside Twin Fabrica. So within this window, you can, of course, review the geometry. You have in the right panel a list of the different entities that you have. You can perform some visualization like a rotated geometry. You can even set a clip plane and show the inside of the geometry if you require, and change also the plane that we are displaying. And we can, of course, also just by clicking, select one of the domains and hide them, just in case we are, for example, interested in seeing what's inside the geometry. And not only we have this, let's say, visualization and also review options, but we also have some Boolean operations that we could perform, such as let's join two of the entities, or let's just remove some entity which might not be interesting for our modeling. The second main component that we need for the finite element analysis is a mesh generator. And in that case, we're actually discretizing the physical space of the geometry. And that means that we are transforming our partial differential equation problem into a set of ordinary differential equations that are more treatable. The user has two options to actually start a project from Twin Fabrica, which is done just by clicking on File and New Project. And you can either select to import directly your step file, that then you can use your inbuilt mesh generator tool to create your tetrahedral conformal mesh, which is suitable for thermal simulation. Or you can also import directly your mesh file that has been extracted from third-party platforms such as COMSOL Multiphysics or ANSYS, or let's say also GMesh. However, I would also want to mention that we are quite flexible in this point, and although step files and mesh files are the ones that our customers typically use, we are also flexible in developing parsers for any specific file formats that you may require. It would just take us a couple of weeks for development and extensive testing before we can actually put it in a new release and give it back to you. So as you can see, if we click this button, we also see the mesh of the component. Colors are a bit more difficult to see because we do have some fine detail on the winding hairs. But that will be it for the second component now. And as you know, we are just missing now the problem definition. So we need to define now the material properties of our geometrical entities, the heat sources that can be found inside our component, and the boundary conditions. And this can be constant, they can be also time varying, they can be space dependent, temperature dependent, or they could even be defined by a mathematical expression. Those expressions can be introduced in the mathematics section, and in the case, for example, which is the case for this model, that you have some mathematical expression that defines the power losses in your magnets, then you would just come here, write the expression manually that you know it's a custom expression, and then in the heat sources you would define a boundary, a power loss for your magnets that is referencing that mathematical expression that you wrote before. And let's say that after we have completely defined our problem with the material properties, so defining thermal conductivity, specific heat, and densities of the different entities, heat sources in all the component, and boundary conditions that are taking some effects, we have completely defined our finite element problem. And what we can actually do now is go and build the form. So it's done simply by clicking this button, and within some seconds, it will take less than 1 minute, you will see that this button actually what it does is generate the full order of matrices. And these matrices are sparse matrices and must be solved, and that's why we have also integrated in the tool our custom finite element model solver that handles those sparse matrices. Once the model is built, the operation, as you can see, it took 17 seconds approximately, and it completed with success. It built the full order matrices of size, as many nodes as we have in the mesh. And for this project, we actually have 260,000 nodes, as you can see depicted here. And that's the size of the sparse matrices that we have just built. However, in order to solve them and to visualize a solution, we have incorporated this tool, this form simulation tool that we can click. And when it opens, we can simulate both steady state and frequency domain conditions and visualize the solution within this pop-up. So on the right panel, again, we have the geometrical entities present in this geometry. Again, we have some basic visualization options. We can hide some domains if we are just interested in the inner part. And on the left panel, we have all the parameters related to the finite element model definition. So we have the material properties defined for thermal conductivity, specific heats, and mass densities. And we also have all the parameters related to the heat sources and boundary conditions. Now, it might seem a lot of parameters, but we have certainly introduced a lot of mathematical expressions for the different power losses of the magnets, windings, stator iron, and so on. But let's simply take a look at the speed, ID, and IQ values, which have this specific value here. This value can, of course, be changed. And once we change it, we are satisfied with the parameter configuration that we have selected. We can actually go on compute. And within some seconds, we will be able to visualize the temperature across the entire domain, or in other words, actually, at all the mesh nodes that we have in the geometry. We can see that certainly we do have a good definition of the temperature, and just to check that we do have temperature in all the mesh nodes, we can hide some entities. And if we're just interested in the particular temperature of one point, because we know, for example, it's a hotspot, we can at any moment come here, just place our mouse, and it will tell me that that point is at 164 degrees Celsius. We also have integrated the color bar here at the right for you to know approximately which ranges of temperature the model is having, but this would be for the finite element model simulation. And I'd say up until this point, Twin Fabrica might seem just like any other finite element analysis software. But here's from this point where we bring competitive advantage. And in traditional finite element analysis software, the models are complex and slow to process, which limits their real-world applications. And as you can see, as we were seeing before, this model actually has 262,000 nodes, which in practice represents 260,000 equations that need to be solved in each time step, which is very impractical for embedded applications. But Twin Fabrica actually solves this by reducing the complexity of the models. And here's where our unique approach to model order reduction comes into play. So we can move to the reduction tab. And I wanted to mention that while software like SimCenter or ANSYS can handle finite element models well, they can't reduce the model for real-time or embedded applications. With Twin Fabrica, thanks to our proprietary model order reduction, we can handle complex thermal simulations that can also contain advection terms with the CFD, in which the velocity of the fluid has been characterized and imported in Twin Fabrica, and even temperature dependencies. These are dependencies that most other software simply cannot address, and this positions us to deliver highly complex models that can be embedded for real-time applications and represent real component behavior very accurately. So let's say that we have a reduced order model, and just with a simple click here, actually, we would start to build it. It will now certainly take some time, but we can go back to the model that we already have. And once we generate the reduced order model, we are certainly generating a reduced set of differential equations that replicates the full model with high accuracy. That means that actually what we will have is a model varies with high fidelity to the big one, to the full order one, with a reduced number of equations. As you can see, the model that we currently have has only 39 states, and compared to the one of the full model, it has been greatly reduced. We can at any point calculate what is the tolerance that we have achieved. In this case, we have set it up to 1 e-5, and thus making the reduction very effective and very, let's say, very close to the real model that we are taking as benchmark. This step certainly takes about 10 to 15 minutes. It really depends on the number of degrees of freedom that you have, and also the model that you have, the geometry, how many nodes you are also having, because in each of the steps of the reduction, you are actually comparing the reduced model with the full order one, and you are accomplishing or ensuring that the tolerance is below your set criteria of 1 e-5. So once we're done with the reduction, we can assess the robustness of the result, and that we also provide a visualization tool to solve, let's say, the reduced set of equations, which again has passed from 260,000 equations to only 39 equations, and that tool is within the statistics button. And yeah. In the tool, you will be able to see how it does, or you can perform sensitivity analysis to observe the behavior of the reduced model compared to the full order one. Okay, so, but even with, let's say, with the reduced model, even with it, there is a challenge, which is that when you take this model to the test bench, it might not match perfectly with real-world measurements. And it is because the model is nonlinear and it has some unmodeled effects that come into play. So, for example, you have non-material properties, you have time-varying boundary conditions, simply missing inputs like, for example, the inlet temperature of the fluid or the coolant flow. If you don't have that information, those inputs really have a big effect on the thermal response of the model. And this is where Twin Fabrica has its second competitive advantage. We are delivering a two-level calibration. In the next step, so in the calibration tab, we can actually perform what we call the physics-based calibration. And we start by calibrating the reduced models parameters based on real-world test bench data. The data has been, let's say, recorded from your component of interest, which in this case is an electric machine, but it could also be a power inverter, it could be onboard charger, or many others. And in the test bench, we have placed some thermocouples and we have recorded the temperatures. It could also be with either cameras, for example, or any other measurement equipment. But the important step is that we actually record the data and import it into Twin Fabrica. So the data we import into Twin Fabrica will be a set of inputs and outputs that define the thermal response of my model to certain inputs. It will be a transient data. And for example, in this case, my inputs are going to be the ID and IQ currents the speed in revolutions per minute of the rotor, and the outputs are going to be the different temperatures that we have recorded with thermocouples in the motor itself. And yeah, then let's try to start the calibration. And just give me 1 second. I'll just move to a slightly powerful machine. So let's just take it from where we started, actually. And if we start the calibration, you will see that certainly what we have on the plots is how the different parameters are being tuned within Twin Fabrica. So we can see that on the top graph, we have a set of parameters that the user has configured for the finite element model definition. Those parameters include the material properties, include all the parameters related to the boundary conditions and heat sources. And what the Twin Fabrica is currently doing is using our inbuilt ordinary differential equation solver to solve an inverse problem, and it finds the best set of parameters that perfectly match the experimental measurements that you have recorded in the test bench, so in the real world measurements. And just to comment a little bit, you can see that there is a kind of, let's say, a sort of dance of parameters that are being moved from a lower boundary to an upper boundary that the user has defined. And by solving this inverse problem, we can actually see what is the best parameter snapshot that we achieve with Twin Fabrica, and that the output of my reduced order model really matches the experimental measurements that we have introduced in Twin Fabrica. So as you can see on the left bottom graph, we have a cost function, which is the 10th logarithm of the root mean square error, and it's slowly decreasing. At some point, it will come to a saturation, so to a convergence, in which we will see that it's not decreasing anymore. So far, we have 70 iterations, and we still see that it's decreasing. So we can actually leave the calibration for, let's say, 150 or 200 iterations. But then on the right graph, we see that we have some detail of the error statistics. And we can see that we have the 0 error mark here. And the goal is actually that all the 4 sensors that we have in the electric machine, which are twin the magnets and twin the windings, get as close as possible to the 0 error mark that we have here. So again, this will certainly take again 10 to 15 minutes. So I'd say we can actually stop it and use the calibration that we had previously done. We would just leave it until 200 and then use that calibration. But we can stop it, and that'll be it. So I also wanted to mention that these parameters that include the material properties of the model, as well as the factors defining the heat sources, it's not the values, sorry, the heat sources are not the only ones that we can tune. So for example, in the case before that I mentioned that, let's say I don't have information of my inlet temperature. In that case, we can still give that parameter to Twin Fabrica, so we can configure it in the boundary condition. And since we will not update it or will not upload it in Twin Fabrica together with experimental measurements from the test campaign, Twin Fabrica will understand that that specific boundary condition, so the inlet temperature, will need to be tuned. So even if we have some unknown parameters or some power loss distribution inside the component which is unknown, we can use Twin Fabrica to tune certain parameters, which will actually be tuned and give the best output, an optimal output that gets as close as possible to the experimental measurements that we have uploaded. So let's say once we are satisfied with the accuracy, we can actually stop the calibration process after, as I said again, 200 iterations approximately, and we can validate the model. So if we move to model validation, it will open a new window, and we can just make it bigger. We can run the calibration instance that I was showing, And we can see a comparison of the experimental measurement, which is the solid line, compared to the output model of Twin Fabrica, which is the dashed line here. So we have some configuration here, but it's important to note that this is not only the calibration tests, but also the validation one. So all the tests that we have imported in Twin Fabrica. We have some options here that it lets us select all the tests that we can. We can also plot, for example, let's say only one of the tests, but all the 4 thermocouples that we have inside. And we are already seeing that we might have some problems. So while it was possible, let's say, to match all the tests very accurately, some of them still have, I would say, some dynamics that were not properly tracked with physics-based calibration, or even some bias in the error. And as I mentioned before, Twin Fabrica provides a 2-level calibration, and it means that our challenge doesn't stop at the physics-based level. And in real-world systems, you know, boundary conditions can be time-varying. We have set Twin Fabrica to just tune a value for the inlet temperature. And the system's behavior can change due to unknown parameters or just some unmodeled effects and some parameter dependencies that we just didn't know. And for this exact challenge, we are using a discrepancy model, which is a nonlinear data-driven model designed to couple with these nonlinearities that we have in the system. This proprietary neural network architecture guarantees stability and is very easy to use. For that, you would just go to simulation, discrepancy training, and you'd be able to just select 3 hyperparameters and then click on train. And after you have configured those, you will see that it starts tuning the parameters of the reduced order model until, let's say, a loss function value is also achieved. Very close, or let's say very similar to the one from the calibration. This function also will get to a saturation point in which it's also not getting lower. And that's the point in which we should actually stop our training. And this step certainly takes a couple hours because it's indeed training a machine learning model that adapts to unknown parameters, dependencies within the model. And that is why we are actually not going to launch it. And we will simply use the discrepancy model after the one that we trained before. And the result that we get after training the neural network is a trained reduced order model that not only reacts to physics that have been set up and trained in the physics-based calibration, so in the first level, but also a model that can adapt to nonlinearities, time-varying boundary conditions, and temperature-dependent parameters. So in order to check the accuracy, we can actually move to the simulation panel and select our simulation slot number 1, which is the first row of the simulation panel, with the reduced order model that has been only calibrated with the physics-based. So let's say only the stage 1 calibration. And let's just select the test that we were seeing before, test number 8. You can see that just within some seconds, it's able to simulate a 10-minute test. And these results are exactly equals to the ones that we were seeing before. So indeed, we see that the dynamics are not as well tracked as they should. We also can see that certainly within the test, there was some kind of change here that made the temperature change. So maybe some time-varying boundary conditions, maybe some power losses that were not identified, or we just don't know what happened, let's say, in the test bench, but our model certainly with the physics-based calibration was not able to correct it. Instead, in the simulation slot 2, we can actually plot the same model, but in this case, coupled with the neural network architecture that we just trained, and of course, with the same test. And you can see that it takes the same amount of time, so in less than 1 second, it simulated the same. And if we plot all the 4 signals, we can see that in this case, it's able to track it much better. So we don't have that error bias anymore. And we certainly see the dynamics of this of the sensor that was placed in the windings in this case is very well tracked. So To this point, I would say that we are quite satisfied with the accuracy that we obtained, and the only thing missing would actually be to use this model, right? So we would need to explore it. But before, I want to say that the temperatures recorded in the experimental measurements, so let's say these 4 thermocouples that we have between the winding and between the magnet, have only been used now for the physics-based calibration and the discrepancy model training. However, I wanted to mention that users have full flexibility to add as many sensors as needed to the output of the model with a simple dynamic selection widget. So if you go to calibration and sensors, you will actually see a full geometry and be able to set as many sensors as you want, so that not only you have the 4 sensors that you have used for calibration, but also be able to export the sensors that you want. So this feature offers the user full control over sensor placement, and it enables the monitoring of critical temperature points or areas of particular interest within the component, which, for example, define your current derating strategy. And it doesn't mean, so having reduced the model from 260,000 equations to 39 doesn't mean that we cannot place those sensors. We can certainly place sensors in all of the mesh nodes, and they will just be an extra model output that we need to compute, but which, again, it's just 39 equations. It can be done in real time. So for the export options of this model, we actually have 3 different ones. If we go to File, Export, we can select Project Model, which are the state space representation of the full model, or the reduced one, the one that we select. And those matrices can actually be exported and enables the user to implement them in the target platform of choice. And then we also have the Simulink model, which is a white box model ready to be integrated into your simulation environment for model-based design. And we also have the C code, which is meant for embedded systems. And it allows you to optimize the numerical representation of the model parameters to maximize the execution efficiency and generate optimized C code ready to be plugged and played. And this one is ideal for testing, for example, under real world conditions with real-time feedback. So just to give you some example, I can certainly, if you go on export and click on Simulink model, with just a couple of clicks, you will be able to export the Simulink model like the one that you're now seeing on the screen. It has the complete configuration of the inputs. You can see that we have some boundary conditions here with the ambient temperature, the inlet. We have our speed, our ID and IQ currents, and we also have the temperature of the permanent magnet and the windings that serve as inputs, since you know that the power losses really depend on those temperatures. So just with a simple click, we get this full model, which has the input configuration. It has the reduced order model in this side, and it also is coupled with the discrepancy model, as you can see in this block here, which acts as a correction to the output of the reduced order model. So as you can see, we are taking the output of the reduced order model and adding a correction that will form our full model ready to be exported. And we can open the simulation scope, and we do have all the signals here. But if we click on run, if my thing actually ready run, yeah, it was actually quite fast. Yeah, if we click on run, which is actually immediately done, we can see how all the signals, we have comparison of the experimental measurements, the ROM output, and so the reduced order model output, which has only been physics-based calibrated, and the one also that is coupled together with the discrepancy model. So just for the sake of clearness, we can plot the third signal, which in this case, we have the measurement, we have the reduced order model output, which doesn't get, which has this error bias, but then with our discrepancy model, which is able to cope with the nonlinearities and model defects, we are able to get very close to the real value that we have measured in the experimental campaign. So let me close the Simulink model, and just as a recap, or also before, I also want to mention that for as a summary, and just to give you some numbers, for the C code export, we exported for this very same model and implemented it into the Infineon RX TC3X evaluation board. And the numbers that we got is that the code ran in less than 100 microseconds. It used less than 1 kilobyte of RAM and less than 40 kilobyte of flash memory. And this makes the model fully suitable to run in the 10 millisecond tasks of the microcontroller, which is a requirement that typically some customers come with. And just as a recap, Twin Fabrica offers high-fidelity physics-based models, which are real-time feasible through model order reduction. We offer flexible sensor placement that even if you don't use those sensors for calibration, and even if your model has been very reduced, you can still export any of the temperatures into your mesh nodes. And we have a dual-level calibration with a physics-based and data-driven approach that handles nonlinearities and model defects and time-varying boundary conditions. And we have seamless export to Simulink, C code, or the state-based representation of the model. And again, I wanted to mention that this was not a full demo of the software. It was just a showcase of the main operations that Twin Fabrica performs. But if you would like a deeper look in the software or a personalized demonstration, we are very happy to schedule an individual session with you. So thank you for your time. I'd like to give the word back to Andrea, and we are happy to hear any questions that you might have.
Thank you, Alvaro. Thank you, Alvaro. Thank you, everyone, for your attention.
Great. So we do have a question from, let's see, we open the panel. Yeah, so from Ibrahim Abdallah, thank you for the presentation. Sounds like an interesting approach. Thank you very much for your participation. In the example you showcased, you used PMSM. Have you compared the tool's results with the testbench results for another machine type, such as EESM? Yeah, we certainly have worked with many machine topologies, also with different cooling scenarios. Yeah. We do have tested with different machines, and even just to give you an example, we have tested both wire jacket cooling, also oil sprayed cooling, and the results look quite promising. And let's say our customers are also satisfied with them. Let's say that our approach is independent of the machine topology that you use. And if all the data is ready, you have a good, let's say, geometry, you're ready to mesh it with a tetrahedral conformal mesh or use our inbuilt mesh tool, and you have all the data from testbench recorded, you can use our tool to actually get to the very similar results that I was showing you before. I hope I answered the question. I go for the second one. And do you have results under dynamic load cycles rather than just operating points? If it's the case, how would that affect the calculation time? Yeah, we do have the data as well. Like for other cases, as I said, this was just a showcase, so didn't want to go much into detail. But we also have some dynamic cycles that even took I would say for 20 hours, in which the complete operation of the machine was changed in terms of speed, ID, IQ, boundary conditions, fluid was changed, fluid was cut. So really changing very dynamically the behavior of the model. And again, the model is completely real-time feasible. Of course, in case that you are simulating 20 hours, instead of just taking a couple seconds, maybe it takes 1 or 2 minutes to simulate the complete cycle. But it's not, it's something that, let's say, something reasonable. So it's still completely real-time feasible. Okay, does the full order model allow CFD? You showed liquid cooling channel, but can it handle through ventilation and rotation as well? Yes, we can import the CFD solution into Twin Fabrica. And not only you can import, let's say, the the velocity of the fluid, so velocity map of the fluid, but you can also import another maps such as the heat transfer coefficient map if you have it, and the full order modeling as well as the reduction will take it into account in the calculations, and you will be able to have as well the model with that input with, let's say, for example, the inlet temperature and the coolant flow as input, and you will be able to change it dynamically within your system. We have another question. Do discrepancy correction cope with functional safety? We do have, so the discrepancy correction is actually just, let's say, a model that is together with the output of the reducer model, and we guarantee stability at all points. So yes, it is always guaranteed to be stable, and it copes with functional safety. It would just react as if it was not there, and let's say just correct the output of the reducer or the model. What computer hardware is required to achieve multiple modeling times, assuming parallel clusters are needed? Certainly, we typically use with our laptops, which are quite office standard. Of course, it depends on your model, and I'd say the bottleneck typically is on the rendering. If you have, so we are used to work on models which have a lot of nodes, even millions. We're talking of models with 25 millions of nodes, and we were able to handle them. But then you might see that the rendering of the geometry is a bit slow. This is something that we, let's say, that we allow the software to do, since let's say it's something very reasonable that your software is slowed down if you upload such a big model. However, if you have such a big model, of course, you will need a computer or a machine with good RAM, let's say, which is probably the bottleneck. And we do use some parallelization, but only if it's available. However, I'd say your experience will be very much improved if you do have a parallel course, which I think is the case for any modern machine. Also, if you have a dedicated GPU, we actually also leverage it, and we can also reduce the computation times in the different processes within the software.
Okay, in case, of course, you have any additional questions, please feel free to drop them in the chat. Before logging off, we wanted to, of course, share with you what kind of ways we are offering to our customers to test the virtual thermal sensing technology. We developed two different programs that you can see on your screens to support the different level of engagement. The first one is our Twin Fabrica Sandbox environment, which is perfect if you want to test the platform autonomously and see and follow the workflow end to end. And we will be providing the models, so it fits very well for, let's say, an initial and low commitment evaluation of the overall tool. Then we developed a more, let's say, intense program that is called the Innovation R&D Pilot. This program is a joint development initiative where we collaborate on together building a thermal digital twin of one of our customers' real and strategic components. We define the KPIs, we integrate the test data, we validate the model with the physical sensors data, and we support also the embedded implementation with the C code generation, let's say. Of course, if you'd like to, let's say, have a more in-depth assessment of the technology, this is the recommended path, and we have seen, of course, more satisfaction in considering the fact that, of course, we will be using and inserting your personal components and data within the software platform. For sure, we will share all the recording. We will share the informations that we showed in the slides. And of course, in case you'd like to understand better how the platform works, understand better the programs that we can potentially present and embark together, we are happy to collaborate from now onwards.